Okay, let's start. So the question I posed at the beginning is, as you get older, do you become more or less independent from your guardians? More or less independent? More independent, right? So what does that mean? What does it mean to be independent? Do more things yourself. Okay, you don't have to worry about what your parents' plans are for tonight. If your parents are painting your room, like right now, if they're painting your room, that affects what you're going to do tonight. You're not going to do your homework in your room. But as you get older and you move out, if your parents paint your room at your room at your parents' house, that doesn't matter. You're still going to go out and party, right? Because that's what you're going to do anyway. That's what independent events mean. If you've got successive things going on and they're independent, anything that happens previously won't affect anything that comes afterwards. Our learning intentions are to identify events that are independent from each other. Okay, we're going to have more than one event. So like event A and event B, how do we know that they're independent? And we're going to also derive a formula that can help us test for independence of events. And we're going to get that formula from our definition of conditional probability. In fact, I'll write down the definition of conditional probability as a formula on the board so we can keep track of it. So here's the formula. The probability of event A given event B follows the formula, the probability of event A and B happening divided by the probability of event B. Okay, event B is the reduced sample space, so that's what we divided by. Our success criteria is to be able to identify independent events and also to apply a formula to quickly determine whether events are independent from each other or not. Independent events. So let's consider an example where we do have independent events. I'll read it out. To understand independent events, we consider the example of flipping a coin twice. This is an example of two events happening one after another. We give the letter capital A to be the event where the second coin is head and B is the first coin being a head. And we're asking the question, what's the probability of A given B? Which means, what's the probability that the second coin is a head, given that you know that the first coin is a head? I'm going to give you a moment to just have a think about this. What's the probability that the second coin toss is a head if the first coin toss was a head? What's the chance? Imagine it. You toss a coin first and you get heads. What's the chance that the second coin toss is also 1 in 2, right? Think about it. The first coin toss does not affect what your second coin toss is. They're independent events, and we can prove that. Okay? And what I'm saying is that the probability of the second coin being a head, given that the first coin being a head, should be the same as just the probability of a second coin being a head. They should both be a half. So let's prove that. The probability of A given B. The formula should be the probability of A and B happening at once divided by the probability of B happening. In the numerator, we've got event A and event B happening at once, which means what's the probability that the first coin is a head and the second coin is also a head? So that's the case where we have a heads-to-head situation. And that's a 1 in 4 chance. There are 4 different combinations of 2 coins, but both of them being a head is 1/4. If we divide it by the probability that the first coin is a head, which is 1/2, we get 1/4 divided by 1/2. And you can probably see where our answer for this question being equal to 1/2 comes from. So let's work it out. 1/4 divided by 1/2. I write it using the division symbol, so I can use my trick to turn it into times. 1/4 times 2 over 1. And you can see that 2 over 4 is the same as 1/2. So to summarize, the probability that the second coin is a head, given that the first coin is a head, is 1/2. We've shown that mathematically. But that also means that the probability of the second coin being ahead, given that the first coin is ahead, actually didn't matter what the first coin was. So you could have easily rewritten it as just being equal to the probability of the second coin being ahead. I'll write this formula up on the board. If A and B are independent, then the probability of A given B is just equal to the probability of A. Okay? Doesn't matter whether B happens or not. It's still going to be the same probability. So that's where our conditional probability comes in. It's this at the bottom. So I'll read it out. The probability of the second flip showing heads does not seem to be affected by the outcome of the first toss. This is an example of independent events. Two events are independent if the occurrence of one event has no effect on the probability of the occurrence of the other. Okay? I've been saying the same thing for the last few slides, but that's the important bit. You need to understand what independence means. At the bottom, we've got a different formula, which looks different from our previous formula. And now I'm going to show you how we get this. First, I'll state it out. This is telling us that events are independent if the probability of their intersection is equal to the product of their individual probabilities. In fact, that's important. I'm going to write it down, and then I'll show you where it comes from. This line that I've just written down will be the most common equation that you'll be using in this current exercise. Okay, so where does it come from? We start off with our definition of conditional probability. Okay, we start off with this. And then we know that if we have independent events, then that conditional part reduces to just the probability of your event happening, whether or not your condition has occurred. So I can replace that first part, see the part that I've underlined? I can replace that part with just the probability of A, because it doesn't matter whether B's happened. If it's independent, then I can rewrite this as at the next line. Okay, so that becomes, the right-hand side stays the same. And then I'm going to group together PR of A and PR of B. And this is where the formula comes from. Okay, once again, we did that because we knew that if the events are independent, then it doesn't matter whether your condition has happened or not. The probability must stay the same. Okay, this becomes a test of independence. For example, if they give you a pair of probabilities individually, and they also give you the probability of their intersection, you can tell whether they're going to be independent or not. Multiply these events individually, and if they don't equal to each other, then they're not independent. If they do equal to each other, then they are independent. So it's like an equation to test for independence. Independent events compared to mutually exclusive events. If you understand what mutually exclusive events are, it might seem similar to independent events. So just briefly, two events are mutually exclusive if they have no elements in common. As a Venn diagram, those circles are separate from each other. At the bottom, we're stating that events that are considered mutually exclusive, so it's like this case, cannot also be independent. The way I'm going to explain this is the fact that if things are independent, then one happening does not affect anything else. So let's consider this case where you've got mutually exclusive events. And I'll pose this question. If event A is satisfied, can you also get event B? are there anything that are in common? Can both be satisfied at the same time? No. Okay, so in fact, something happening has affected something else. If you've rolled an even number on a die, then that's affected whether your answer's odd. If your roll is even, then it can't be odd. So they're not independent with each other. So I'll restate this. Things that are considered mutually exclusive cannot be independent, because if you satisfy one event, then it affects the other event. In fact, it just makes the other event impossible. So, another way to state it is that things that are mutually exclusive, the probability of their intersection is 0, because there's nothing, the null set, there's nothing in the intersection. So if you try to apply the same thing to independent events, and you know the probability of the intersection is 0, then that's implying that one of your two probabilities are also equal to 0 as well, which doesn't make sense. If you're considering the odd rolls and then even rolls of a die, then they both must be more than 0, which means these two things can't be happening at the same time. Good question. So I'll repeat the question that Andrew has just asked. If you're throwing a coin twice, then the outcome of the second throw is not affected by the outcome of the first throw, if you're just flipping it in the same way.
Yeah.
But with the dice example that I gave earlier, you're just rolling the die once. So if you get an even number, that must mean it can't be odd. Okay. Yeah. Thank you for bringing that up. I should have made that more clear. First example, two events A and B are such that probability of A is 0.3, B is 0.1, and the intersection is also 0.1. Are A and B independent? This question asks, does the probability of A change if B has happened first? Now, if they are independent, then it should follow a certain rule that I've had on the board. Any ideas of how we can answer this question? So please have a look at the rules that are placed on the board. One of them is a test for independence. If it satisfies the test, then it is independent, otherwise it isn't. Roman?
If the probability of A times the probability of B
Okay,
is equal
PR.
to the probability of A intersection B, then it's independent.
Yeah, if they're equal to the intersection, then they're independent. So can you just tell us right away what this is? The product of these numbers?
It's just 0.3.
A 0.03, right? So as you're working out on a test, you should state what these values actually are. So 0.3 times 0.1 is 0.03. That 3 moves one place value down. The intersection is a 0.1. And you can tell that they're not the same as each other. So first, you figure out their values. Then you state whether they are equal or not. And to state that they are not equal, you use the equal sign with a slash. So this is stated that the left-hand side and the right-hand side are not equal, and at the end you state the answer. Are they independent? No. Okay, 3 parts. 1 part to get your value, 1 part to reference a formula, and the other part to answer. I'm going to give you a moment to copy this down before we move on. So here are some bonus questions that aren't in your notes. I reckon they're important because if you're given information that events are independent, then you can actually figure out their intersection. If things are independent, then the intersection is just the product of their probabilities. So here's an application where you're trying to find the union of A and B, given A, given B, and given that they're independent. I won't ask you to copy this down because they're not in your notes. But to figure out this question, I apply the addition rule. So somewhere along the line, I'm going to make a mistake. Where's my mistake?
Minus.
Minus, okay. You all know this anyway. So A is 0.5, B is 0.1, but they don't give us the intersection, or do they?
0.05
2 times A and B, and the key word here is that they are independent. So once you know that they are independent, plus turns to minus, that gives you your third value. Okay, and the end, it's 0.6 take away 0.05, which is 0.55. So that's a way, that word independent gives you an extra value. Another example is where it's the same question, but events A and B are mutually exclusive. So being mutually exclusive implies that they don't have anything in common. If we wanted to figure out the union, okay, once again, addition rule. I can actually also tell what the intersection is. If there's nothing in overlap because they're mutually exclusive, then what's the intersection? If you know, just please call out. What's the probability of the intersection? 0. Right, there's 0 because there's nothing overlapping. So it's impossible to get something that satisfies both events. In this case, your answer is just 0.5 plus 0.1 minus 0, and it's 0.6. So I'll repeat once again, these words are important when you see them because they give you extra information. We've got this two-way table. 165 subjects volunteering for a medical study are classified by sex and blood pressure, which can be high, normal, or low. If a subject is selected at random, find the probability of n. So let's work that out, the probability of n. You've done these sorts of questions already. The probability of the n would be the total number, regardless of whether they're male or female, divided by the total number of people, which is 165. And then you want to simplify this. If you can tell that the common factor is 11, you can divide both of these numbers by 11, which becomes 4 out of 15. That's example A. Example B, find the probability of the intersection. I think what's important to write down is actually write down the total numbers. So let's add these together very quickly.
120.
120? Yeah?
45.
45 and 165. Okay. You've done this already. Great. So the probability of the intersection F and H is F and H, that's 11 out of 165. And it turns out that they're both divisible by 11 as well. 11 divided by 11 is 1, and 165 divided by 11 is 15. Question C. Find the probability of the union of F and H. PR, F union H. Okay, so the probability of the union is, well, how do we figure this out? We can apply the addition rule, which is, so I'll write it down. The probability of F plus the probability of H, and we minus the intersection to account for the people that's counted twice. Okay, so let's figure this out. The probability of F was 45 out of 165. We add on to that the probability of H, which is 99 out of 165. And we take away the intersection. And we found that out earlier. I'm going to use the number 11 out of 165 because they're already common denominators with the other fractions. So let's add these numbers together. 45 plus 99. 144. And then take 133. Great. So it's 133 out of 165. So to test whether this fraction can be simplified or not, I know that 165 has the factors of 5 and 15. No, 11 and 15. and 133 can't be divided by 5. Sorry, 133 can't be divided by 11, and it also can't be divided by 15. So I leave it as that fraction. Okay, that's question C. Question D. Find the probability of F happening given L has happened. F given L. So I think in this case, 12 out of 22, F given L. Right, so it's the probability of both happening out of the probability of the condition. That's 22. This was questions from the previous exercise, basically. So it becomes 6 out of 11. Right? Yeah, okay. The probability of getting someone who's low blood pressure, given that they're female. So low blood pressure, given that you're choosing the group of female people. L given F is 12 out of 45. I think that's divisible by 3. 12 divided by 3 is 4. 45 divided by 3 is 15. Okay, notice the answers for question D and E. Even though the letters for F and L are switched, the answers will be different because your conditions are different as well. We're at the end now. Are F and L independent? There's 2 ways you can prove this. In fact, there are 3 ways. First, you can compare the conditional probabilities for F and L and see if it's equal to the probability where if the condition wasn't given. Okay, that's one way. I'll do that way in a moment. The other way is to compare the intersection between F and L and see if it equals to the product. If they are equal, then they are independent. But before we use these tests, it's not that clear. So let's use one of these. I'm going to compare the probability of being a female with the condition of being low blood pressure. PR, F given L, we already know is 6 out of 11. Now let's consider the probability where the condition isn't given. What's the probability of just choosing a female? PR of F. PR of F. There's 45 females in total out of 165. 45 out of 165. I can see here that both of these numbers are divisible by 15. So 45 divided by 15 is 3, 165 divided by 15 is 11. Okay, let's compare these numbers. The probability of picking a female given that condition is 6/11. The probability of just picking a female without any conditions is 3/11. Does being low blood pressure affect the probability of choosing a female? Yeah, it does. It does get affected, which means these 2 events are not independent. If you're going to separate all the people into a group that are just low blood pressure, then you're going to have a higher probability of picking a female from that. Okay, this is one way to do it. The other way to do it is to use that next formula. So if you know the probability of the intersection, F and L, have we already figured that out? F and L. No, we didn't. So let's do it anyway. That's 12 out of 165. The probability of choosing someone that's both female and having low blood pressure would be the 12 people out of 165. The product of those, F times L. F times L is the product of females, that's 45 out of 165 times 22 out of 165. So what you can do here is evaluate the right-hand side And when you do, you can see that the number for this isn't the same as the number for the intersection. In other words, the right-hand side and the left-hand side are not equal, which means that they are not independent. So at the end you can write, using either of these two tests, not independent. In the previous examples, we're basically doing experiments where there are two stages. So first picking a female, then checking whether they're low blood pressure. Or first picking the low blood pressure group and then seeing whether they're female. This is an example where you're just drawing one number from that group. So it's a one-stage event, but you can still tell whether they're independent or not. An experiment consists of drawing a number from this group, 1 to 8, A's from 1 to 4, set B's the odd numbers, and set C is 4, 6, and 8. Are A and B independent? We're going to be once again using one of your two rules. I reckon this rule, the intersection, is going to be easier because I can tell what the probabilities of those individual ones are. So let's actually write it out first. The probability of selecting a number that satisfies event A is the 4 numbers out of the 8 in total, which becomes 1/2. The probability of B is also 4 out of 8, which is 1/2. For event C, it's 3 out of 8. All we've got to do to test whether they're independent or not. Yes. All we've got to do to test whether they're independent is to multiply their probabilities and see if it equals to the intersection. So that means we've also got to figure out the intersection. So let's figure out the intersection of A and B. The probability of the intersection. Intersection means numbers that occur in both events at the same time. So let's compare events A and B. How many numbers repeat? Yeah, 2 of those numbers, because I can see the number 1 and the number 3 repeats. So that's 2 of those outcomes out of the total of 8. 2 out of 8, which turns out to be 1/4. That's the answer for the intersection. Now let's find the answer for the probability of the product of the probabilities. So we know from previously it's 1/2 times 1/2, which is 1/4. Okay, let's compare these numbers. The intersection is 1/4. The product of their probabilities is also 1/4. Are they independent or not? Yeah, they are independent. From our answer, they are independent. But what that means technically is it doesn't matter whether event B is satisfied first. The probability of getting event A is still the same whether or not B's happened. Or the probability of getting B is the same whether or not event A has happened. Okay, so these are independent. Therefore, you'd write at the end, PR A intersection B is equal to their products. It's very important to write this because you're telling me how you know that they are independent, and then you can say, yes, they are independent. So it's a three-step question. How about, yeah, Sasha?
I was going to say, can you do it that way? Like, can you write the second bottom line first and then work it out? No, one more down. That first and then work it out, or write it again?
No, I wouldn't write this first because before you work out their values, you don't actually know whether they're the same or not. If they are the same, then you write the equal sign. If they're not the same, then you have to put a slash through those equal signs. In fact, there's a bit of time. How about you go through questions B and C and test whether they are independent or not. And then I'll place the answers on the board in a moment. So I'll just answer these. I think the answers were no, and for question C it was also no. I'd like to wrap up this lesson by stating in another way why understanding independence is important. So let's think back to our example of getting defective boards from an old machine or a new machine. If you're getting more defective boards from one machine compared to another, that means having a defective board is dependent on your old machine compared to a new machine. So if you're the boss of a manufacturing plant, you want to know whether the age of the machine is affecting the defectiveness of the board or not. You're going to see a lot more examples on independent events as you work through this exercise. Try and answer this question to yourself. Can you identify independent events or not using a formula?